Hey everyone, so we just finished talking about both kinematics and forces and how they kind of relate to this idea of rotation, how we can kind of rework them in order to make mathematical representations of what's going on. We can do the same thing when it comes to energy. And for the most part, we're actually going to do a lot of the same tricks that we did before. If you recall, one of the things I said is that we could take a lot of these equations and rework them so that they actually are rewritten in terms of the rotational versions. Now, as far as derivation, like where are these derivations coming from, a lot of it comes from the fact of the conversion factors. For example, if we take the angular velocity equation, the one that looks like this, omega naught plus alpha t, if I multiply each term by r, because whatever you do to one side of the equation, you do to everything. Well, omega r we know is velocity. Omega naught r would be an initial velocity. Alpha r is just acceleration, and then we have time. So we end up with the exact same equation. So a lot of them come from the relationships that we have between the linear and the angular values. Velocity versus angular velocity, linear acceleration to angular acceleration, and using that in conjunction with the already established uh, linear equations. Not to mention, most of these equations also come from the standard definitions, which again are very similar to the idea of linear motion. So these aren't just popped out of the sky. They actually have physical definitions. I'm just not going into too much of the derivations, and I'm kind of hand waving it when I say replace it with their angular counterparts. But we can actually do something very similar with the energy. So we could first think to ourselves, what are some rotational equivalents to energy? Well, there's actually two. So you might think that since we have a lot of potential energies, we have spring potential, we have gravitational potential, maybe we have rotational potential energy. Unfortunately, no. That actually, I'm going to explain that in a little bit. But the main type of rotational energy that we're going to actually talk about is actually rotational kinetic energy. If, you know, kinetic energy is the energy of motion. So for an object that is rotating, it is in motion. So we can talk about its rotational kinetic energy. And we're going to denote this as k rot or rotational. The format is actually very similar to the translational version. So if you recall, the kinetic energy for translational, when it's moving side to side, is 1/2 mv squared. So like I've said before, m turns into I, v turns into omega. So the equation we end up getting is 1/2 I omega squared. Now, it is actually extremely important that you put these subscripts underneath there because we're now going to have to deal with multiple kinetic energies. We didn't have to worry about this before because originally when we're only talking about the linear cases, there was only one type of kinetic energy. Maybe there was an initial or final, or maybe we might have actually had kinetic energy coming from multiple objects, but it was all the same type of kinetic energy. But now that we have rotational kinetic energy that has to be taken into account, we're going to want to make sure that we're constantly asking ourselves and reminding ourselves, is the object moving along the floor? Is it rotating as it moves along the floor? And we're going to have to put the kinetic energies depending on the scenario. Now, I said before that, the potential energy might have been a good guess for the type of rotational energy we have since we have so many types of potential. And the answer to that is kind of a yes or no type thing. See, one of the things I sort of mentioned when I talked about the energy, again, I did mention it, but I kind of hand waved it, mostly because I didn't want to go into too much detail with it. But what we call the potential energy, the gravitational potential and the spring potential, is actually a simplification of the work being done by those forces. Now, if you recall, I mentioned that we have work, which is the change in the energy of the system. That any force does work. Now, just for simplicity, I actually mainly used work as a way of describing the work being done by a person, or sometimes the work being done by an engine, basically some outside force. It turns out that the gravitational potential energy is actually just the work being done by gravitational potential. When we lift an object up to a height, the object doesn't just gain potential energy. I mean, we say it does, but what's really happening is that by lifting it up to some height and allowing it to now be able to fall because of gravity over some distance, the gravitational force is going to do work on the object, pulling it down, which then gets converted into kinetic energy. Similar thing for the spring potential. When we pull the spring out, it doesn't just gain the potential out of nowhere. What's happening is that we're doing work on the system so that when we let go, the spring force can now do work on the block itself, like within the system, to change the kinetic energy of the block. So what we call the potential energies are just variations of the work equation. I did sort of show this in how I actually derived the equations. I said before that, where's my, that if we want to talk about the work being done by the force of gravity, work is force times distance. So this would be the gravitational force times distance. Well, that's just mg times a vertical distance, which we call h. So that's where that comes from. The spring potential was a little bit weirder because we had to actually look at the graph. So this was force versus distance, and then the work was the area under the curve, which was 1/2 fx. But since F is not normally something that we automatically can tell with the spring, we replace that with 1/2 kx times by x, and that's where the 1/2 kx squared comes from. There was a so we're gonna actually not talk about just potential energy, but we're actually just going to talk about rotational work. And again, this has a rotational version. So like I said, rotational work is force times distance. So we're just going to replace the force with tau and the distance with theta, and we get this. Now, I actually did want to mention that even though I've been, setting up a lot of these conservation energy problems where we're looking at the potential and we're looking at the kinetic, and I kind of treated it as something different. There's actually a concept in physics called the work energy theorem, which basically just says that work equals change in kinetic. Basically, the idea that whenever you do work, you're changing the kinetic energy of the object. This kind of goes with that idea that if I drop an object from some height, the work being done by the gravitational force turns into kinetic energy, or the work being done by the spring turns into kinetic energy. So that's kind of where it kind of comes from, but not necessary. Like I said, you can answer pretty much any question by believing that there's a separate energy of UG, compartmentalizing that with the spring force, and work as three different things. All right, so here's the first question. Pause the video, work itself, and we'll go over in a second. All right, so the first question, it wants to know just the rotational kinetic energy. So again, we are going to use our equation, 1/2 I omega squared. They give us the rotational inertia, so we don't have to do any calculations. We just plug the numbers in and we chug out our answer. So we should get 675 joules. All right, here's the next one. Pause the video, work itself, we'll go over in a second. All right, so they want the work being done, so we're going to use tau theta, and because tau is just force times distance from the pivot, then we're going to replace that with FR theta. The one thing that we have to pay attention to, one full revolution, that is 2 pi radians. So my work is going to be 5 times 3 times the 2 pi, which gets me 94.2 joules. All right, here's the next one. Pause the video, work itself, and we'll go over in a second. Now they want to know the rotational kinetic energy of this system, and they give us this rotational inertia for the fans, right? So what we're going to do is this. Um, we're going to have 1/2 I omega squared, and that's the kinetic energy equation. And then we're going to set it equal to 1/2, and then we're going to plug in the 1/3 mr squared omega squared. Now, uh, there's a few different ways that I can set this up. One thing I can do is I can treat each one individually. So I can find the kinetic energy of one of these propellers, because if you actually pay attention, the propeller is made up of the wind turbine is made up of 3 propellers, each one with a mass of 300 kilograms, and each one rotating at this rate. So what I could do is I could separate this into 3 parts, where I just kind of calculate the energy of one propeller and then multiply it by 3. If I wanted to, I could have actually sort of maybe multiplied the 1/3 by 3. But what I'm going to do is I'm just going to multiply the mass by 3. Uh, really doesn't matter. So the rotational kinetic energy is going to be 1/2 of this rotational inertia with 900 kilograms as the total mass, 30 being the length of the beams. And then we have 30, I don't know why there's 2 times, but 30 times 2 pi over 60. Now the reason I have to do this is because the 30 is in revolutions per minute. Now, one of the things that you could do is remember that 1 revolution per minute is 2 pi over 60, or just pi over 30. But the way I always like to do it is just replace the words, replace the units with their radian second counterparts. So for example, revolution, 1 revolution is 2 pi. So that becomes 2 pi in the numerator, 2 pi radians. And then minutes, well, there are 60 seconds in a minute, so I replace minute with 60 seconds, and I end up getting 30 times 2 pi divided by 60 seconds. So that's the easy way of doing the conversion, but there's a bunch of other different ways you could do it. It's whatever floats your boat. But when you do this, you end up getting 1.33 times 10 to the 6 joules. All right, here's the next one. Pause the video, work self, and we'll go over in a second. All right, so here they want us to calculate the change in the kinetic energy of the pulley. So the change in kinetic energy, well, there are 2 ways that I could do this. Like with everything, a change in kinetic means that I could just do final kinetic minus initial. That requires me to know the final angular speed and the initial angular speed. But if I read the question, I don't know either. I can actually assume that the initial angular speed is 0. I didn't really clarify it in this question, but otherwise, if it wasn't 0, you wouldn't be able to answer this. So there must be another way to solve this. And the way we're going to do that is by realizing that this change in kinetic energy is coming from work. So we just do the rotational work being done on the pulley, set that and say that that's going to be equal to this change in kinetic. So we do same thing that we did last time, tau theta, replace the tau with FR, plug our numbers in. We get do the same thing where this is 3 rotations, so it's going to be 3 times 2 pi, the number of radians in 1 rotation, and we get 226.2 joules. All right, here are the next 2 parts, so pause the video, work self, and we'll go in a second. All right, so for part B, like I said, couldn't be answered if we didn't believe that the initial angular speed was 0. So what we're now going to do is actually take advantage of that idea that the amount of work that we did is equal to the change in kinetic energy, which is just final minus initial. The initial is 0, so I can actually say that the change in kinetic is equal to the final. This, I do want to point out, is extremely important to constantly note. Don't just get into the habit of assuming that the change in kinetic is going to be your final. I've seen this happen a lot where people will do something like this. Well, actually, we'll do something like acceleration is just velocity divided by time. and they'll take whatever the final velocity was divided by time, and they'll say that that's your acceleration. Uh, that works only in the cases where the initial velocity is zero, because acceleration is actually the difference in these velocities. So just note that, because if there was an initial speed, I would have to make sure to take that into account. I'm only dropping the delta because the initial kinetic energy is zero and the initial energy speed is zero. So I do 1/2 I omega. I plug in the 1/2 mr squared into there, and then I plug in chug, and I end up getting that the final angular speed is 6.73 radians per second. For part C, finding the linear speed, this is just basically converting this number. So I use my conversion factor, V equals omega R, plug my numbers in. Since we're looking at a point at the edge of the pulley, I put in 2 meters, and I get 13.45 meters per second. Uh, I should point out that it is important to note where the point is that they're referring to. Uh, Remember that with angular speed, when an object's rotating, the angular speed is the same regardless of the point along the item. So if we have a disk rotating, a point at the very edge and a point very close to the center are all rotating with the same angular speed, but their linear speeds are different. So if you're doing a conversion, don't automatically assume that the r is going to be the radius. The r is the distance of the point to the center. In fact, it's important to note that a lot of the r's in these equations, I haven't really been specifying them too much, but they do kind of mean different things. In the r in the I equation, the 1/2 mr squared, or all the other rotational inertia equations, those are physical dimensions of the object. Like, they are the actual radiuses of that object. But the r in the conversion equations, like V equals omega R, or the torque equation Fr, that's not necessarily the radius of the object. That's the distance that point that we're referring to. A certain point in space or a point on the object is from the pivot. So sometimes the r could just mean how far away is this from the pivot versus what is the actual radius. All right, I just wanted to clarify that. And here's the last one. So pause the video, work itself. I'm going to go over a second. All right. So here we have a merry-go-round, very common one. Once again, it's going to be turned. They give us this equation, and we want to know how far does the person end up having to run in order for the merry-go-round to turn at some rate. Now, as I mentioned before, we can always kind of approach these questions in a linear mindset of, what would I do if this was moving in a straight line? We apply a force over some distance and it goes to some final speed. How far would we have to go? And that can kind of like help set us up with an overview of what things have to multiply. I could do the same thing here. What I'm going to end up doing is uh, it's going to end up gaining some kinetic energy, and it's gaining that kinetic energy due to the work that I do. So it's very clear that I'm going to do work equals kinetic. So I use this equation. I'm going to set the Fr theta equal to the kinetic energy equation, because I'm using the rotational versions. So 1/2 I omega squared, I plug in the 1/2 mr squared for I omega. I could actually do a few more things with this if I wanted to. Like, I could actually, actually no, you know what? That's, I think, all I can do. Oh, I can actually drop out the r's. Um, I don't do that here, but there are a few things that you could do to try to simplify a little bit. And what we're going to do is solve for this theta. So we plug our numbers in, and we end up getting that theta is 2.817 radians. Now, for the most part, this question is a little bit ambiguous. It's not clear exactly what we're looking for. You could give a radian degree, like a radian angle, or as a how far they actually ran, but that's not really useful. I mean, how many radians is that? Like, I don't know what that is. And someone, depending on the size, of course, they might have had to run further, but cover the same radian. So this normally isn't what we would consider for a question like this of saying, well, how far is it? Um, so I would say if this was a multiple choice question, you would have to look at your choices and see what kind of units they're giving you. If they're giving you units in radians or at least no units at all, then this would be a fine ending point. But most likely they're going to want you to convert this. So we're going to use the S equals theta R, multiply this by 2 because the person's running along the edge of the merry-go-round, and we end up getting 5.63 meters. So now this is actually something that we can visualize. This is going to be about um, a little bit over 15 feet. So we can actually already tell how long this child has to run for, or how far it has to run for in order for this merry-go-round to reach this speed. Right? And that's pretty much it. So that was the first part where we just have practice using the equations. We wanted to practice plugging the numbers in. The next part that we're going to talk about, we're actually going to see how this can apply to conservation of energy. If you recall, in the energy unit, that was kind of the main aspect, was not just, hey, can you calculate potential and kinetic by themselves, but how do these energies relate to each other? We sort of kind of did it in the first part with, setting work equal to kinetic, but we want to go into a little bit more detail than that. We want to do what we were doing in the other ones where we have objects falling off of buildings and energies being transferred into multiple different types of other energies. So that's what we'll do in the second video. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.